non-inertial frame of reference, different observers will actually identify different forces. So for an inertial frame of reference that is outside of the Earth and can notice that this person is rotating, they're going to identify these terms for the force on the spring. Whereas an observer that is on the surface of the Earth and doesn't even realize that it's rotating, they will just simply identify the gravitational force for the force of the spring. Now, the force on the spring is just going to be a number that the scale is going to give. So both observers are actually going to read the same number on the scale, which then just tells me that I can say that Fg equals F that big M causes on small m minus this extra term that appear because Earth is rotating. So now let's identify who these terms are. Well, this one, this F of m on m, we're going to call the true gravitational force. That is the one that Newton identified as m on m as gravitational constant times the mass of the Earth, the mass of the person, divided by the radius of the Earth. This other one, on the other side, the one that is experienced by this person here, is what we call the effective gravitational force. Finally, this other term is that fake that we someone call centrifugal force. Right? That force that isn't real, but that we experience due to the fact of being in a non-inertial frame of reference. Now, does this mean that now we need to go back and change all of our calculations to always include this extra term? Fortunately, the answer is no. So let's take a look at what the free fall acceleration is going to be now that we know all this extra information. Well, my free fall acceleration near the surface of the Earth is still going to be Fg divided by m, which then if I use this equation is just going to be F m on m minus m omega squared over r times r divided by m. For this F big M on small m, I can use this expression from the gravitational force. So this small m is going to cancel this other small m. This small m is also going to cancel this small m. And I'm going to be left with something like this. Big G, big M, radius of the Earth squared. I missed this square here. Minus omega squared times radius of the Earth. Now, notice that all of the constants that I have here are just actually things that we can go and measure. Gravitational constant is just a number that you can look up. Mass of the Earth, big M, you can also just look at the number. The radius of the Earth, we can look it up. Omega squared, remember that is the angular velocity of the Earth, that 1 revolution per day. And again, the radius of the Earth. So these are all numbers that we can actually look up and plug in here. Now, let's give this whole term a new name, which, for example, is going to be G of Earth, right? The real acceleration due to this gravitational pull of the Earth minus omega squared r. Now, if we go and plug in all these numbers, we're going to get that this is actually 9.83 and some more digits minus 0.03, everything in meters per second square, which turns out reduces to the 9.8 meters per second that we know and love and that we've been using all this semester. So things get a little more complicated when we go away from the equator to a different latitude, but the bottom line is the same. If we assume or we decide to treat this fake centrifugal force as a real force that is just pushing us away from the center of the Earth, then we can say, well, then my effective force is going to be what I've been measuring all this time, and then I can keep using G equals 9.8 meters per second squared which is the value that we've been using all this time, and everything's going to be fine.